Last time we talked about column pivoting. Why did we talk about column pivoting? Why was there a need for an improvement of our simple Gauss algorithm? We saw that for some input, our simple Gauss elimination process will fail. And then we had an idea and we improved our algorithm. What is the next step? The next logical step in the side of a mathematician is, can we crack the new improved algorithm? Are there systems where column pivoting fails? And unfortunately for us, this is true. We can find such a setting. And this is such a setting. Basically, this is the same system for which the simple Gaussian elimination process failed, but the improved column pivoting did not fail. But what did we do? We multiplied the first line with the factor 10,000. And then out of a very small number, very close to zero number, we get a 10. And this 10 is more than 1, and so column pivoting will not take part. 10 will be the largest element here in that column, so we will use the first line. This is minus 10,000, and so we will add a large number to this one, and this is not a good idea. So let's check what will happen here. Starting with that system and doing the Gaussian elimination, we use the first line because the 10 is larger than 1, so we'll use the first line to kill the 1. What do? First we copy the first line, and then we take the second line and add a multiple of the first line. In that case, we add minus 1 divided by 10 times the first line. So 1 minus 10 times that is a 0, the desired 0. And here in that line we get 1 plus 1,000. So it's 1,001. And here we get 5 plus 3,000, which is 3,005. So this is the exact solution. But let's recap what did we do last time. We tried to better understand what's going on internally. We have floating point numbers, so there's a fixed number of digits following the first one. And we assumed that we deal with decimal numbers. That doesn't change so much. And we assumed that we have 3 significant digits. In truth, it's 16, not 3, but 16. But for better understanding, let's do that. So this is the exact solution, and the rounded version, which will always be used using a computer, using floating point numbers, we have 0 and here rounded to 3 significant digits we have 1,000, and rounded to 3 significant digits we get 3,010. Now we forget this line and now we use that line. So we have x2 is 3,010 divided by 1,000, and we get 3.01. But now we use that result in that line, and to make things more easy, let's do that calculation. 10 times x1 minus 10,000 times our x2, which is that number, and that is equal to minus 30,000. And so x1 is minus 30,000 plus 30,100. So we brought that to that side and then divided by 10, and we get our result. Minus 30,000 plus 30,100, we subtract two numbers which are very close together, and that's always a very bad idea doing numerics, because this is a rounded version of the exact result. So here this operation is a really bad idea. So we get 100 divided by 10, which is 10. And so our solution we calculated is that, and the correct solution is that. So I confused these two numbers. Okay. So let's compare. This number is very close to the correct number, but this number 10, the 10 of our solution, is a disaster. And so we are in the same situation as we have been before inventing column pivoting. Due to the multiplication with factor 10,000, our idea, our concept of healing is completely destroyed. And for better understanding, I want to write down our problem we had before multiplying with 10,000. It was that problem. So let's remember what we did before. Gaussian elimination for that problem here was this step, and then we calculated our solution 3.01 and 10, and so this was our solution using simple Gaussian elimination, but this is the correct solution. Then we had an idea we can get rid of the problems if we swap these two lines. Then we do that calculation here, and then we get that solution. And what was the concept? Search in the first column which is the largest entry and bring that line to be the first line, and then do the job. The search for the largest entry took part here in these lines, and then we swapped, and then our problems were healed. As we saw here, these are real MATLAB commands and real MATLAB logic, and here we have a large matrix A, and then in the first 10 lines, the first 10 columns, we used numbers very close to 0, and then we saw that we completely crash with the simple Gaussian elimination process, but we don't crash anymore if we use column pivoting. But now, what do we do now? We have our matrix A. In the first 10 lines, in the first 10 columns, we insert very small numbers. Then here, this is our solution, and that is our right-hand side. And now we multiply these first 10 lines by a very large factor, which is 2 to the power of 50. We do that for the coefficients, we do that for the right-hand side. So the solution will keep staying the same. And now let's use our code. Here we have the code, our simple algorithm, completely nonsense. This number should be 0 or very close to 0. We compare our solution, which we got by using simple Gaussian elimination. Here is the correct solution. We take the difference, we take the absolute value, and we are looking for the maximal entry, and this should be 0. Now we call our column pivoting algorithm, and again this number is not 0. Here it's 34 instead of 6,000, so a very big improvement, but this number should be very close to 0. This number should be 10 to the power of minus 11 or something like that, and not 34. This is a catastrophe. If the correct solution is something like that, and the solution we get applying column pivoting, this would be 10.3 and minus 8.4 and numbers like that, then this solution is complete nonsense, and so our column pivoting fails. This is a very, very bad situation, so our idea is crashed by a counter example. And now we can say, okay, what shall we do? We need a new idea to fix the problems. So, okay, this is our situation. Which idea do you have? Okay, analyzing the situation, how we corrupted the coefficient matrix in the right-hand side, then we can do that if we divide our entry by the sum of the remaining elements. In our case, what did we do? We said, okay, 10 is the largest number, but instead we should compare 10 divided by minus 10,000, which is 0.001. Compare that number to 1 divided by 1. This is 1, so this line will be chosen to be the first line, and if we do that, then we will have no more problem. So we can apply this logic, and this was the idea I had when I was a student. This idea is very good, but it's not so easy. We have a fraction and we need an addition of a lot of elements, so more popular is another idea. I don't think it's really better idea, but it's more easy, and more easy ideas are most times the better one. So a well-known and an often described idea is total pivoting, and that means in the first step, simple Gaussian elimination will use the 2 to eliminate here the 4 and to eliminate the minus 3. Column pivoting will use the 4 because it's the largest element in that column. And total pivoting will look for the largest element in the whole matrix, which is 5. So we will swap line 3 and line 2, and then we will destroy these entries. And to make things more easy, let's also swap these two columns, and after these steps we will kill the remaining entries. So let's see what happens. We start here with that matrix, then we find the 5. So let's swap line 1 and line 5, and then we get that system, and then let's bring the 5 to the first position. So let's swap column 2 and column 1, and we get what you see here. And now take that 5 to kill the minus 1, and take the 5 to kill the minus 2. So we add this line times 1 over 5, add that to the second line, and we kill the minus 1. This will happen here, and then here multiply that by 1 divided by 5, so it's minus 0.6, and add that to the second line, so we get 3.4. And then multiply 3 by 1 divided by 5, so you get 0.6, and add that to 1.5, and you get 2.1, and do the elimination process also for that line, and then you get that line. Then what we do next we examine that block, and we are looking for the largest entry in that matrix. In this case, this entry is here, so we will swap line 2 and line 3, and after that we will swap column 2 and column 3. So after that step we get that, and now 4.2 is the largest entry here in that block. And let's keep track of our variables. If we swap column 2 and column 3, then we have to adjust also that x1, x3, now it's x3, x1. Now let's use the 4.2 to kill the 2.1. What do we need? We have to add the minus 0.5 fold of that line to that line, and doing so we will kill the 2.1. Here we get the desired 0, and this time times minus 1 divided by 2, it's minus 0.4, and adding minus 0.4 to 3.4 is the 3. And we collect the entries as we did before, but we have to be careful if we swap lines here. So we have to do the swapping also for minus 0.2 and the minus 0.4. So having that, we get this matrix. This is a copy of that, but once on the diagonal. And what is our upper triangular matrix? This is that matrix here. This is that matrix. And now what do we have? L times U is A, but not really A, but a modified A. If we did the swapping before the algorithm would have started, that's impossible to know which swapping do we need. We see that only doing our algorithm. But if we had swapped the lines and the columns of A in advance, then L times U will be that matrix B. So B is A, but a little modified by swapping some lines and swapping some columns. We have to keep track of the swapping. 3, 1, 2 is the row index. Which swappings did we do? If that was line 1, line 2, line 3, then after swapping line 1 and line 3, we have 3, 2, 1. And the rows are swapped here again. So we have 3, 1, 2. And this is here. And what do we have here in the columns? We ended with x2 in the first column, x3 in the second column, and x1 in the third column. And that is what we have here, 2, 3, and 1. And now, if we want to solve A times what is B, then we have to do the swapping. So first we have to swap the right-hand side according to that index. So bring the third element to the first position, the first element to the second position, and the second element to the third position according to these indices. And then use the column indices and rename x1, x2, x3 to be x2, x3, and x1. And now we calculate our solution as we did before, and then we will have our desired solution. So here's the code for total pivoting. What happens? I commented out a lot of code, and forget that code. Here we take the block in which we have to find the largest entry. Then here we find the largest entry. The number of the largest entry is not of any interest, but the index is of interest. And here this is some crude MATLAB logic. Don't spend too much time to try to understand. Don't spend too much time to try to understand this specific logic using int to sub. So that is MATLAB detail, very deep details. Using MATLAB a lot of times you will appreciate commands like that, but being a newbie to MATLAB or somebody who uses it very rarely, then you will hate MATLAB for that. Trust in me that this code works. And then we do the line swapping here according to our logic. And after that, do the column swapping. And then we have our modified swapped matrix. Then apply the Gaussian elimination as we did before. And then you have your L and U matrix. But on top to the L and U matrix, we also have to return the indices which tell us which swaps took place. And how do we use that code? First we do the decomposition, then we permute the right hand side according to the row index, and then we do the back substitution, and after that we have to permute our solution according to the column index. So this is our code and it works. So let's check our example here. Here is our example. Here we multiply the first 10 lines with our large factor, and then we try LU simple, then we try column pivoting. We know these two will fail, and then we try our total pivoting, and now we get a difference of very close to 0. So our solution in that case is brilliant. We are very close to the correct solution. Yes, it heals our problem. And if you try to find another counterexample, you will fail. Total pivoting is a very good idea and it will avoid numerical problems. But total pivoting needs a significant amount of time for finding the maximal entry. I think it's not very obvious why this is true, but I try to convince you by the stopwatch of MATLAB, which is tick and tock, and then you can see. And then we will do that for a 100 by 100 matrix, and then we see that total pivoting and column pivoting, there is a factor of 1.67. So total pivoting is close to use double the time of column pivoting. If we try for 500 by 500 matrix, it's also close to double the time. If we try for a 1000 by 1000 matrix, okay, so it's 30% more time, and that is significant. So in reality, we have to ponder if partial pivoting suffices. Are there in reality problems like we constructed to find a counterexample, or is that not true and in practice column pivoting is enough? It heals the problems which occur in reality. And the answer is yes, this is enough. Column pivoting normally is enough, and so professional code, for example, the MATLAB solver, does not use total pivoting, but it uses column pivoting. The MATLAB you will have to spend more than 1000 euro to buy uses column pivoting, and I explained you that normally it's okay, but now we are able to give MATLAB an input and it will return a nonsense answer, as we will see later in the video Clever MATLAB. What I want to do is visualize a little the logic. So what is total pivoting? Let's assume we have a very large matrix. In the first step, we will look for the largest entry in the whole matrix, absolute value, and then the largest entry. And then, assuming that this is the entry, then we swap these two lines, and then we swap these two columns, and then we have that entry in that position. And then we do the elimination process, and after doing so, we have that situation. And then we are looking for the largest entry in that block. We don't care about these entries, we are looking for the largest entry in that block. Let's assume it's that element, then we will swap these two lines, the fifth line and the second line, and then we will swap this column and that column, and after doing so, this entry will be in that position, and then we will kill these three entries. Doing so, we get that, and now we are looking for the largest entry here in that block, and let's assume it's that entry. Then we swap line 3 and line 3, so we keep the order of the lines, and then we swap column 5 and column 3, then we have this entry here, and then we will kill these two entries and we get 0 and 0 again. Then we are looking for the largest entry here, and so on. And here, the first step, the whole matrix was the green block. So that's it. That's what I wanted to say about total pivoting.